pleasure to have now a course by Tomás Grigera. Tomás is from La Plata University and the Institute of Fluids and Biophysical Systems, also in La Plata. He's a CONICET researcher, and in this institute, he's part of the Statistical Biophysics group at this institute. He did his undergraduate studies and also his graduate studies at the University of La Plata. He then was a postdoc at Northeastern University in Boston and then in Rome. And he came back to La Plata, where he's a professor, as I told you. His research focuses on the biophysics of swarming and flocking, as well as glassy systems. So I leave you with Tomás.
Okay, now? Okay. Okay, thank you, Silvina. Thank you for the introduction. Also, many thanks to the organizers of this school for the invitation, but also for taking the trouble to organize this activity, which is very important for us and for the young people here. So I will tell you a little bit about collective motion, and we'll explain what it is. But I intend to, in the title, I changed the title a little bit. I used the Statistical Physics for Biology, collective motion, because I will talk about collective motion, but I will try, or I think that for people not directly interested in collective motion, they can take this course as an example or case study of how, or a way you can use statistical physics to study biological problems. So, I mean, collective motion is interesting in itself, but I think there's more to it. If you step back a little beyond collective motion, we'll talk about things that are useful and interesting to study how you apply statistical physics ideas and techniques to study biological problems. So, collective motion is about a variety of systems. These are some examples. So you have insects, midges. Midges are not mosquitoes, are smaller. Sometimes some species of midges bite, others do not bite, but they are not very friendly anyway. And they form these swarms. There's this kind of clouds of insects floating around or above some reference. In this case, the unfortunate head of this empire. Then there's also bigger insects that move together. There's fish that can move together, birds, and mammals that move together. So in our approach, statistical physics approach, we will try to approach this bunch of systems, very different systems, but we will not try to point out the differences, but we'll try to point out or extract what's common, what these systems have in common, and what we can understand about these common features of different systems. They will not be the same. I'm not trying to say that we will necessarily be able to use the same model for all of these groups, but still, we will try to distill and to find what's common in all these situations, okay? So, when we talk about flocking and herding, we are talking about large group or largest groups of animals. Large meaning hundreds of individuals, maybe a few thousand, which is large for, for human scales and for biological scales, but it's not that large from a statistical point of view, okay? But we'll come to that. So this phenomena can occur at different length scales, from bacteria that move together to flocks of birds or mammalian herds, the buffaloes I showed you. So we have insects, fish, mammalians, And one characteristic of these groups is that they can move in an orderly fashion. So they move together, but they can also change direction quite abruptly in response perhaps to some perturbation or to some change of the situation somehow. What they have in common is, at least, so the cases we will study is that individuals can move. We will call them self-propelled. They move. They are not pushed. They have their own mechanisms to move. They move because they want, let's say, so they can move. No one is pushing them. You don't need interaction with other members of the group for an animal just to move in some way. These groups are not groups that are following leaders, or at least not fixed leaders. So there's not always a chief that's a boss that's telling everybody where to go and what to do. When there is a leadership, in some cases like in foraging, when looking for food, sometimes they follow a leader, but this leader is temporary, right? It changes from time to time. They seem to follow the. So we are looking at groups that are completely horizontal. They don't have any obvious authority. Okay, they're very democratic. And we are looking at situations where there are no external fields. That is, there's no an externally imposed direction where the group must move to. For instance, you could have, due to have the case of migrating birds that have a north, have a direction where they want to go, and so there's kind of a drive which we could imagine as an external field. So it's a drive which is telling a force somehow that is pushing them in a particular direction. Yes, that's not the case we are studying here. We will see that they will order, they will go together, but it's not the direction they will choose is not an external reference. Okay. So, oh, by the way, we will have a time at the end of the lecture for longer questions, but if you wish to ask something for clarification, something you've missed, you can just raise your hand and we'll have quick questions as they come up so that nobody gets lost during the talk, okay? So, in these talks I will be focusing mainly in two cases, which I will briefly introduce now, and I will come back to these. But basically I will be talking about flocking and swarming, okay? And by flocking and swarming, I mean the following. By flocks, my example, my idea of flocks is the flocks of starlings. So this is a starling. This is a bird, also called the European starling. These birds form flocks, quite large flocks. This is photographed. Unfortunately, I don't have videos to show you right now, but you can look up in YouTube this keyword starling murmuration. So these flocks of starlings are called murmurations for some reason. And if you look this up, we'll see lots of videos that show these birds moving together, quite large groups. You will see it's very impressive how they move, how they order themselves, and how they manage to change direction and as a whole. I mean, the flock seems to change direction quite abruptly as a whole. So they are very. The point of here is that this case is the motion is very ordered. All birds are moving together, are coordinating themselves somehow to go in the same direction. Of course, and avoid collision, of course, but they all move together. The flock moves as a whole. The other case, we'll be talking about this, the swarming case, And swarms are groups of insects that basically don't go anywhere. So you've seen this. I'm sure you've seen these groups. You've seen midges, and you've seen mosquitoes. There are other small insects which are not called midges, but you usually see before the light. At night, you see the lights, and you see these small greenish insects just, moving around before the light. So these are swarms. In particular, the experiments I've worked with, the experimental data I have worked with is about 2 or 3 species of European midges, which are these guys, definitely uglier than the birds. And they do these swarms. This is an important part of the mating behavior. So the males do make this group, and they wait, or somehow they call the attention of the females, which will enter the group, and then a couple will exit for mating. This is also how mosquitoes, at least malaria mosquitoes, also do mating, also by making the males making a swarm, and then there the mating takes place. But so I'll be coming to back to this, but the point here is that this is in some sense the opposite case of the swarm, because this movement is very disordered. The group is not going anywhere. All members of the group are flying around, just turning, swirling, going back and forth, but the group does not go anywhere. So this is a very disordered movement. And part of the challenge or the interest of this is that we will try to put together these two behaviors in the same framework, with the same kind of models. Okay? So these are some questions you can ask. Here I'm following mostly Vikšek. In the review I will be quoting at the end. So questions you can ask about this phenomena, which is, well, first of all, most obvious question is, how are these groups getting ordered without following a leader? What's the mechanism that can self-organize these groups into order? Are the motion patterns system-specific or not? So are they characteristic of the species that does the swarming or the flocking, or is there some universal principle where one can understand that leads to these patterns appearing? These groups can be perturbed because of ambient conditions, because, for example, in swarms, you have winds, air currents that perturb and sometimes destroy the group, or you can have predators. Starling groups are known to have attacked by falcons, by peregrine falcon. So the falcon will attack the group, will try to separate an individual from the group to attack this individual. So so the group somehow responds or reacts to these perturbations, and one challenge is to explain how this happens. When the group changes direction, for instance, because there's an attack of a predator, we can interpret this as information propagation. Somehow, a small group of birds sees the falcon, changes the direction, and this change in direction propagates to the whole group. So how does this propagate? How can you explain that? Why do these behaviors emerge? Is there a biological advantage in doing these things, in flocking? For instance, these starlings will do these groups before landing, before getting in the evening. They're going back to the roost, to the trees where they have their nests, but they don't go directly to this place. They just, before doing that, they go around and around and around several times. So why they do that, it's not completely clear. And a little looking at the last 2 points, looking at now from the point of view of statistical physics, physicists, you could ask, so to what extent is the nature, the specific nature of the units, of the animals, the structure and the behaviors of these animals taking part in these movements, to what extent is this nature important or fundamental in determining the phenomenon, in deciding how the shapes and the patterns and the movements and the laws of these groups are. So are they specific to the identity of these particles, or can the same patterns arise in very different groups? In particular, can you do non-biological particles that move the same, that look globally the same? And this one can also observe that under some conditions there's kind of transition that occur. For instance, you have a bunch of pigeons that just are feeding in the ground, just everybody minding the business, and then for some reason they fly because a cat appears or whatever, they fly, but when they fly they order. So these changes from order to disorder can be explained with some reasonable mechanism. So these features, and especially these kind of questions we are asking, in the mind of a physicist, statistical physicist, lends itself to a statistical physics approach, because of several things. But basically because what we see seems to be dominated not by what the individual is doing or wants to do or prefers to do, but by the influence or interaction between many individuals. The group is large, and somehow it is the exchange of information or whatever these guys exchange that will in the end determine the behavior of the group. So the idea that that the groups, the animals are particles that interact, leads to a kind of modeling we are quite used to in statistical physics, which is the problem of treating interacting particles. Okay, so then we say, okay, this is a system of interacting particles. Let's do statistical physics with it. And also because in statistical physics we know that there are mechanisms that lead to the arousal of spontaneous order. This is something that has been very much studied, which is the mechanism of spontaneous symmetry breaking. For instance, in a magnet, you know that at high temperatures, the magnet is the ferromagnet at high temperatures is not a ferromagnet, it's a paramagnet. There is no net magnetization. All the individual dipoles, magnetic dipoles, are pointing in different directions. There's no net magnetization. But at low temperatures, the interaction, a local interaction, can lead to the breaking of the spherical symmetry, the rotation symmetry, and the system will choose a special direction in space and will order, and all the spins, all the magnetic moments will point in the same direction. So this we, in principle, know how to deal with, or is a phenomenon that we know exists in statistical physics, so we can try to use these ideas to explain flocking. And also because when we are trying to, every time one has a new problem, studies something new, what we do is to try to apply something we know. We compare it, to something we know, and try to use the tools we already know, we already understand to explain the new phenomenon, and we change them as we go, as we need. But we don't start over from scratch every time. Yeah, we cannot do that. So we are trying to incrementally build and better our tools and our understanding to explain new phenomena. Okay. So at this point is where once you've convinced yourself that you can try at least to study biological groups, collective moving groups with systems of particles, then the idea of the notion of active matter starts to make sense, because it is clear that, okay, we are going to do modeling of these groups as particles, but it's also clear that there cannot be particles that like we are used to when you study, solid state physics or the physics of liquids, right? So they're just not, we call them particles, but they are units that are very complicated. They have very complicated internal structure. Okay, so they will not be the same as ordinary matter. So they will be active matter. Okay, basically it's active matter because what the main difference, or the difference that strikes the most at first, is that they are self-propelled. They will move even in the absence of other interactions, or they will tend to have a fixed speed independent of other interactions, right? So if you have a particle that's moving in a viscous medium, it will lose energy and it will eventually stop, right? Unless you have a force, unless you have an interaction that can pump energy into this particle. This is not the case here. In principle, you have a bird that flies in a medium with dissipation, which is the air, and can fly as long as it wants with a constant speed. Okay, so that's self-propelled. That's why we will call these systems of matter active matter. Okay. So, but once you get into this label of active matter, then we will use the idea of active matter to think about collective motions of birds and insects, but active particles need not be animals. You can do active particles that are purely chemical. You can devise particles that transform energy with chemical reactions, or more simply, you can put a bunch of particles like rice grains on a plate and vibrate the plates. So you add energy, and these particles will move. Okay, and in that sense, they are active. Okay, clearly they are out of equilibrium systems. So that's another important thing that will come up again and again. These systems are not in equilibrium. That's clear. They are using energy. They are transforming energy. But I mean, will you see these examples? The models we will use here, we are thinking of animals, of birds or insects, but actually the models will not have anything in particular that tells you that this thing is biology. Simply, we know that the particle can move by itself. The mechanism we will not specify. So it could be something that's purely chemical, So it's, in a sense, when you talk about active matter, then the field is quite broader than collective motion, collective animal motion. Okay, and it can get pretty complicated too with many variants. So we will talk about active matter, but I want to introduce this word in this area, but here we will be concerned with biological active matter. Okay, you can do broader things with active matter. As an aside, you have active matter and you have externally driven systems, and in some sense they are similar systems. In both cases, you have an input of energy that sustains the motion of the particles. But usually the word active matter, or the idea of active matter, is reserved for systems where the energy conversion takes place at the micro scale, takes place inside the particle. So if you have a chemical system where you're inputting energy with vibrations, as I said before, or because you're shining a laser on your system and that ignites some kind of chemical reaction that creates movement of the particles, that's not exactly what we are thinking when you're saying active matter, because those cases, the input is at the mesoscale. It's kind of a field, right, that's giving the system an energy input. The cases we call self-propelled particles or active matter are where the system, the energy conversion process or transaction process is taking place within the particle. And in our case, this process is pretty complicated. You know, animals eat and then move. This is pretty complicated. So we are not going to model that part. We are going to focus on scales that are much larger than the single particle, and we'll just take the process of conversion of energy into motion for granted. It's just there. Within the particle, it's just a black box that can take energy from somewhere and give motion, okay? But that's a big difference. When we are going to do modeling, we are going to model, yes, a system of particles, but we have this. Particles will be active, okay? So now I'm going into modeling. I will introduce some general features of the models, and I will speak about a particular model, a simple model of flocking. Let's, before going to details, I wish to list these, points you have to keep in mind when you are looking into models of active particles, active matter, okay? The main differences, the main things to watch out for when comparing to a system of particles in condensed matter. So there's mainly these 3 points. The first is that collisions need not conserve momentum. Because, so, you know, when you model, you do molecular dynamics, you have an interaction that conserves momentum because you will be using the Newton's laws of motion. And every interaction, you know, after a collision, momentum will be conserved. This need not be the case in these kind of systems, because usually there's a medium that many models or most models ignore. So you have a bird or you have a fish. The fish is swimming in water, okay? And so the fish can change direction by transferring momentum to the medium, to water. So, but since we will not model typically the medium, we'll say these particles just move, they will collide, so they will interact when they are near each other in space. They will change the direction in some way, but the momentum need not be conserved because part of the momentum can be transferred to the medium, and I'm ignoring the medium. Okay, so the medium can be put into the model or not, as I said, and this is usually called wet or dry active matters, meaning wet or dry active matter models, of course. So if you ignore the medium, as we will do here, this is called dry active matter, because it's like birds that are flowing, or mammals that are just walking on the ground. They transfer momentum to the medium, but you don't see the medium. The medium is, it's kind of light. It's air. It's not very heavy. It doesn't. It doesn't. What happens is that when I exchange momentum with the air, this momentum is not then, does not create a perturbation in the medium, in the fluid, that will be picked up by another bird that's coming after me, right? Whereas if you are trying to model bacteria in a fluid, in water, then these exchanges with the medium will create flows at scales that then can influence the other bacteria, okay? So this is called hydrodynamic interaction, and it's pretty well known also in polymer physics. And if you want to model that, you have to take the medium into account, and you have to somehow solve the hydrodynamic equation, the Navier-Stokes equations that describe the flow of the fluid, okay? That would be wet active matter. We won't be getting into that, okay? But remember this word, hydrodynamic interaction. Hydrodynamic interaction means that you move. When you move, you perturb the fluid, and then this perturbation in the fluid is picked up by another individual, okay? If you ignore that, then we are doing dry active matter, and you can do it at high Reynolds numbers, basically. So you can do it for birds in air, you can do it. Whereas for bacteria in water, which have a very low Reynolds numbers, then you typically have to take those kinds of interaction into account, okay? Another thing is that interactions can be non-symmetric. Non-symmetric, I mean, they do not have to obey the third Newton's law, action and reaction. Not only because, as I said, momentum is not conserved, but also because the way the animals interact can be, for instance, visually, and it can happen that I am looking to you, but you're not looking at me. So I'm seeing my partner's motion, but he's not paying attention. Okay, so the interaction need not be symmetrical. And also, in these models, you will almost always include some source of noise and friction. This is actually not necessarily different from, I put it here, but this is something that also noise and friction do appear when you do modeling in condensed matter physics also. When you ignore the fluid, you want to, you want to simulate to model particles that are moving in a fluid. You don't want to take the details of the fluid into account, and so you can do Langevin dynamics, right? So you can introduce noise and friction. You can say, okay, there will be lots of interaction here that I will not model because they are too complicated for me, and I will just take them into account as a random noise. So that's the Langevin equation. The particle is moving in the fluid. The particles of the fluid interact with my particle, but I don't know the forces that are involved. I simply add a random force, okay? This is something similar, but the interactions can be more complicated, and the source of noise is not simply the motion of the fluid, but other, interactions, complicated interactions, fluctuating interactions, maybe with other particles, okay? And we will put some kind of friction, explicitly or implicitly, because when you have, this is something we know from equilibrium statistical mechanics, when you add noise, this noise is an input of energy in your system, and so this energy, if you want to be more or less in equilibrium, or at least in a stationary state, this energy that's entering through noise must be dissipated somehow, okay? And so when you do modeling like Langevin equation, or when you introduce a thermal bath in statistical physics, the thermal bath is introduced with noise and dissipation. These things go since we are not in equilibrium, so in equilibrium statistical physics, there are specific rules, which are called the fluctuation-dissipation relations, which tell you if you put certain kind of noise, then you have to put certain kind of dissipation. Okay? Here, the rules are not that hard because we are not in equilibrium. Okay? But it's still true that these things in a reasonable model will go together. Okay? Because you cannot just pump in energy all the time and expect the system to be stationary, right? So you pump energy with noise, but you have to somehow take it out with the dissipation to reach. We will not have equilibrium here, but we do wish to have a situation which can be stationary, right? Which is what we more or less observed. The motion of these groups can be considered for short periods of time more or less stationary. Okay. Well, these are already the other point. Energy I've already talked about. So self-propulsion needs to be sustained by an energy source, which can be introduced in the bulk or the boundaries in driven matter, or as we will do at the particle level. Biological active matter, this energy is introduced at the particle level, typically with a very simple rule that will tell you what the speed of the particle is. Okay. And the final ingredient that can appear is that interactions need not be metric, meaning the following. In equilibrium systems, the interaction, the force between particles depends on the nature of the particles, but depends quite importantly on the distance between the particles. Okay? So particles that are farther apart interact less than particles that are near. Typically, the interaction goes away in sufficiently fast that one can say, okay, if particles are farther away than some cut-off radius, cut-off distance, they just don't interact. They don't see each other. And this is what we mean by short-range interactions. Okay. So interaction ranges can be limited by distance, but in some cases it's not limited by distance. For instance, insects are known or are thought to interact mainly through noise, through sound. So they sense each other's presence because of the sound. And sound at those scales is damped, is attenuated, in distance. So in swarms of midges, of insects, it's probably reasonable to assume that the interaction is metric, meaning that insects will listen to insects that are within some distance, some cut-off distance that will depend on the species and the condition, but they will listen to insects that are close by. They will ignore insects that are farther away. But in other cases, like in birds, the interaction is visual. At the scales of a flock, vision has no problem with distance. I mean, if it's daylight, you can see, pretty far off. So the limit there is not how far you can see, but how many birds you can keep track of, because the flock is quite big, and so you can't keep track of everyone in the flock, and so you keep track of, 2, 5, 7, 10, around 10 neighbors you can keep track, but not more. So that's what I mean by cognitive or a perceptual capacity. But if that happens, then it doesn't matter how far away they are. So you can interact with your first, say, 5 neighbors, independent of where they are, if they are far or they are near. Okay? So this is called topological interactions. They are not metric. It doesn't matter how far you are. What matters is that I can keep track of my first neighbor, my second, my third, my fifth neighbor, not more than that. Okay? And if you think of it, this rule that you will always interact with, say, 5, 7, 10 neighbors, is also non-symmetric. Because I can be your first neighbor, but maybe you are not my first neighbor. Okay, so especially that's especially true if you are in the border, right? If you think of the individuals and the border of the group, so you have an individual here, then this might be the first neighbor, and this will be the second neighbor. But this guy, the first neighbor, is this guy, right? Not the individual in the border. So these topological interactions will lead to non-symmetric interactions. Okay. So we are ready to introduce flocking models, particularly one model. And let me say, actually the logical flow would be here to talk about experiments, learn more about experimental results, and then attempt to model. That's what you should do. First, look at experiments and then model. But to talk about experiments, I need to do an introduction about correlation functions, which I will do the next lesson. And that will leave me with only one exercise class, because I will not talk tomorrow, I'll talk on Wednesday, and Wednesday there's no exercise session. So I prefer to introduce models now, so that we can, if you're interested, we can discuss a little bit more about models. I will give you an exercise in the exercise session of today. Okay, and then we go back to experiments. But before modeling, you should look at experiments. Okay, so let me introduce the simplest characteristic of the simplest flocking models, and then we will focus on one of them, and you will work, if you choose to, you can work with this particular model I will explain. So we were talking about flocking models, where here flocking, the term flocking is used loosely as just simply individual units that are moving coherently. The history of modeling of flocking or motion is quite long. It became, at first, apparently it was done by computer scientists that were interested in computer vision and generating computer graphics, like in movies, generating with computers groups that could move that was in the 80s. But then it was also attempted by biologists and by physicists. Usually the assumptions are basically these ones listed here. So we will assume that particles are very similar to each other. Actually, we will assume mostly that they are identical to each other. That they move with constant speed or almost constant speed. That's how we will introduce activity. That they can change direction pretty easily. Okay, so they go this way and they just can turn without much problems. So we don't worry very much about how a bird changes direction. We just assume it can do it, and the guy can do it fast. We will assume that they're interacting ways that we specify, but that basically lead effectively to an alignment of directions among neighbors, among first neighbors at least. Okay, and then, well, I already said, they will be subject to noise of varying intensity. Okay. Within these assumptions, there are basically two big kinds of models that you will find if you look into this literature. So there are the particle models, which we'll be looking at in a moment. Microscopic, in quotes, in the sense that we will define an elementary particle for this kind of system, so that's why they're microscopic. Or there are continuum models, field theories, which we call mesoscopic. So these are just continuum models, there are no particles you have fields like in hydrodynamics, like in the Navier-Stokes equations. You can model these systems as just a fluid, a complicated fluid, an active fluid, without talking about the identities, worrying about the identities of particles. And this is useful for when you want to analyze large-scale properties. Okay. The most famous here is probably the Vicsek model, which we'll talk about now. And in this other category, the Turner 2 field theory, which is the field theory that describes the Vicsek model, is probably also the most famous. Within the particle-based models, so microscopic models, you can do, as I said before, dry and wet models. So you explicitly model the fluid, the individuals moving or not. We will do dry now. And you can do continuous time or discrete time models. So continuous time means that basically you write a differential equation that describes the dynamics. And discrete time, as we will see in a moment, you just give a rule. So time moves in steps, and you just give a rule that gives you the dynamical state from one time step to the next. Okay. And we will be talking about models that try to explain or reproduce order arising in these systems. It might be worth distinguishing polar models and nematic models. Polar meaning it's an order where all particles have a head and a tails are aligned and heads are aligned. All heads point to the same. So the direction is one, but all the heads point in the same sense. They all move together. Nematic order means you have particles that are elongated. They can have a head and a tail, but if they have a head and a tail, they align. They are parallel to each other, but sometimes some heads point one way, some heads point the other way, so they move. They don't move as a whole, okay? But there is some order that's developing. Okay? And sometimes you can just model particles that have no head, no tail, and that just move randomly that way or the other way, but always along a particular direction, okay? For instance, for cells, for cancer cells, you might try to do that. Yeah? So cancer cells are elongated, and maybe we want to mainly move in that direction. So let's go to one concrete model, which is the model that I will propose you for your exercises. If you want to try this, you can write a simulation for this model. This is one of the oldest. This model is from the early 90s, and perhaps it's the simplest of these all. The particles only have a position and a velocity, so they're very simple. And the only interaction that there is velocity alignment. And so the model is described by these two equations. So you have position. This is a model in discrete time, and so all particles have velocities. With these velocities, you use to update the positions. Okay. But before updating the positions, you update the velocities. And the velocities you update using this rule, which is each particle looks to its neighbor. So you define a radius. So you define a sphere of interaction. So within this interaction radius, the particle, you look at all the velocities of the particles within this radius. You compute the average of this velocity, and the particle will set its velocity to this average with a noise. So this this operator here means you take this vector, which is the average, you take this direction, and you apply a noise with some amplitude. So you have this vector, and then you randomly rotate them within a solid angle. Okay, this is a little bit of noise. And then you normalize because V naught, so all particles will have the same speed, always the same speed, V naught. okay? So if the noise is 0, if this parameter is 0, then what you have is that each particle aligns to the mean velocity of its neighbors. Right? With some eta, this is just the solid angle where the noise. So the particle wants to align, but it's not perfectly accurate in this alignment. It will just make a small mistake and will not be precisely aligned. Okay. So you can do so that definition is in general dimensions. You can do it 2 or 3 dimensions and 4 dimensions. I suggest that if you do the exercise, you start with 2 dimensions, and in 2 dimensions it's a little bit easier. You can describe the particles with the angle. So the velocity will be V naught, cosine and the sine at each step, and this is how the angle evolves. So you compute the average of the velocities, and you compute the argument. So you compute the new angle, and you add a noise. Okay. So this is a graphic depiction of the model. This is the particle I'm looking at. This particle looks at all the neighbors, computes the average, and then sets its velocity. Each particle does, so all particles do this simultaneously, update the velocities, and then they change the positions. Okay. Yes?
In the previous slide. So the noise there is a vector, right? Because
yes,
you are summing to the average vector, and then you are taking the argument. Okay.
Yes.
So it's a random number between minus eta pi and eta pi in the 2 directions independently.
Yes, I think I was going to talk precisely about noise variance. Probably I didn't. So I wanted to write a different thing here, but there are 2 things you can do. You can first sum all the vectors, get a direction, an angle, and then add a random angle. That's called scalar noise. Okay. And then you can do what is written here, but it's actually more clear here. You compute the average, and then you sum a vector. Okay. And then you normalize. And this is called the vector noise. The idea is that in one case you are trying to model the individual gets sees the velocities of the neighbors right, but then fails to align to it, so you add a scalar afterwards. And in this case, you are saying, no, I'm not seeing the right velocity. I make a mistake when I measure the velocity of each of my neighbors, and I add some small error for each neighbor I'm trying to measure. So basically, that's you can do intermediate things, but those basically the main noise rules. So the original, the scalar noise was the original rule introduced by Wikschek himself, and then like 10 years later, Chaté et al. Introduced this vector noise, which can be written in either of these 2 ways. The interesting thing here is that when you look at this 1 over an I here, so since this operator is normalizing the vector, then you can take this n, you can take it outside, and what you see is that you are introducing this, making the interaction non-symmetric, because when if you look at a pair ij, so okay, I sees j's velocity, j will see i's velocity, but here this pair factor it's different for I and for j. So this is an additional source of asymmetry. Okay, so you will implement this model in the exercise session if you wish. And which you can see with this model is that depending on the amount of noise, the model will give you order motion. So to measure order, you have to define an order parameter. So I did not see in the pointer, but okay. So phi up there is the definition is like the polarization. You basically sum over all the directions and then take the modulus and divide by n. So it's the average direction. If the system is disordered, then this quantity will be rather small. You are basically adding random numbers, so it's order 1 over square root of n, so it's a small number for a large system. If the system is ordered, this will be of order 1 because you are adding very similar vectors, okay? And depending on the noise, the amplitude of the noise, so the amplitude of the angle you add to the velocity after you computed the mean, okay? If this value is very high, you have disorder. If the value of the noise is low, you have order. So you have a transition that looks very much like an order-disorder transition, like what you see in an icing model, for instance, okay? This is the noise. This is the density. So you can study the transition as a function of the noise, but you can also study it as a function of the density. If you have enough particles that within your interaction radius that you can measure, you can compensate for the fact that then you have a high noise. So high density gives you also more order than low density at a fixed noise. Okay, and again you have this kind of curve. I'm pretty confident that you can set up a simulation and reproduce this curve. But this model is peculiar in that there is an interaction between velocity and density, because since the order depends on density, if a local fluctuation, makes so that locally the density increases, then locally the density could be above the critical density for ordering at that noise. So locally the system will order. But once the system is ordered, it will tend to stay ordered because they will travel together. Okay? So this small heterogeneities in density, which you always expect, but in this model, they tend to build up. And this creates an instability. And this is quite peculiar to this kind of models. And it's related to the fact that you can see this transition in 2 dimensions with a model that's not an Ising model, it's more like a Heisenberg or XY model. So it has a vector, right? And so in statistical physics, it is known that you have what is called the Mermin-Wagner theorem, which will tell you that in 2 dimensions, if the order parameter has a continuous symmetry, like XY, okay? If you're in 2 dimensions, then you cannot have long-range order. Yeah. Here, in active systems, you can have long-range order. And part of the reason is this interplay, this coupling between density and local order, okay? So the thing is that even if this is pretty compelling and it's very nice because this is giving us order from a simple rule, from a simple alignment rule that we see in the Ising model or in the Heisenberg model, this interaction with this coupling between velocity and density makes things more complicated. And this simple picture of order-disorder transition is actually not quite right. And it turns out that if you go to very large systems, these instabilities will make, within a range of densities, will make you these bands, ordered bands appear that can coexist. So there will be regions of order coexisting with regions of disorder. Okay, so if you, the current consensus on this is that the phase diagram is more complicated than that simple order disorder things, and it looks more like a fluid transition where you have here a disordered system, Chaté calls it gas, then you have an ordered liquid, okay, so polar order, and here in between you have coexistence between order and disorder in a way, in a fashion that's called microphase separation, because it's not that you have all the ordered particles on one side, the disordered particles on the other side, but you have bands, which, so you have order, disorder, order, disorder, order, disorder. Okay, so this is the red line in here. Okay, now this is more or less the consensus after a very long discussion among several groups that lasted at least 15 years, because even if you have a first order transition in the thermodynamic limit, that is for infinite systems, this is another it is also known that to detect this first order transition, you have to go to large systems. If your system is small, then the phenomenology you see is as a continuous transition, as an order disorder transition. Okay, and this is very relevant because, well, you have to put the numbers here, but you see, okay, so this I missed. Okay, so this is the x-axis. Sorry, so this is as a function of density, and this is as a function of V naught, and you can see that for low densities, so the red and black curves are for 2 and 3 dimensions, but if you go to low densities or to low speeds, the size, this L star is the size at which you start seeing the transition as first order. You start seeing bands and the microphase separation. And you see this size, if V naught or the density is small, this size can get pretty large. And this is very relevant because we are used in statistical physics, we say, no, the results we want are the thermodynamic limit because the systems are typically large. There are many, many particles in a system, like 10 to the 23 or something. But this is not true in biology. In biological groups have 100,000 particles, not more than that. So finite size effect, and we'll come back to this in the next lecture, finite size effects are very important. So even if the phenomenology of the model from a statistical physics point of view is that of first order, when you apply this model to biological groups, it may well be that you are in the region of size here such that what you observe is actually second order or continuous transition phenomenology. Okay? So this is important because of what, when I will talk about experiments, I will mostly interpret what happens with midges as a second order transition. Okay? And we'll be referring to the Vicsek model. And we can say, okay, but how can you do that? Vicsek is first order. Okay, it's first order if you go to large systems. Okay? So, because to be first order, I repeat, you need to generate density, so heterogeneity is in density. You need the density to be heterogeneous. And this will happen more probably for larger systems, okay? If your system is small, or if you can come up with another mechanism that will hinder the formation of these heterogeneities, then you will stay in a second order, a continuous phenomenology. Okay, we come back to this. And another thing to look. Okay, sorry. Another thing to look for is the role of B naught. I'm not talk very much about B naught because it seems that it's like a parameter is just, you know, it's like the length of the spin, yeah, you know, in XY, which is 1, which is irrelevant. Actually, it's not irrelevant. V naught is a thermodynamic parameter in the sense that if you change V naught, you change the critical value of the noise. Okay. So the transition changes place. The phase diagram changes the shape. Okay. And here, just to put it clearly, we generated an ordered system. No, the red system. We change the velocity, we lower the velocity, and it disorders. And then we change it back again, you know, and it goes back to order. So V naught seems an innocent parameter. Like seems that you can set it to 1 always, but it's not. And when you think of it, it makes sense because when the particle moves, it doesn't matter whether it will go out of its interaction sphere, right? So if V naught is very large, it will see a set of particles, but in the next step, it will move very fast and will look at another set of particles to interact with, okay? So that's where activity, so V naught activity enters in a non-trivial way in these models and these phase diagrams.
But what if you keep fixed V naught divided by the size of the interaction, of the radius of interaction?
Well, then no, you change it. Yeah. So I'm thinking that the size of the interaction is my unit of length. So this is one. With respect to that, a large or small velocity it matters. Okay. Yeah. So this is what I propose you to do. If you wish to do the exercise, then you can implement this model. I can help you do it in the programming language you choose, you prefer, and you can do this exercise. You can measure the order parameter as a function of the noise, of the density, and of V naught, and you can play with that and find how the system goes from order to disorder. You can compare noise rules if you wish, and if you feel bold, you can try to try different sizes and try to get first order or second order phenomenology, yeah, by using Binder cumulants. I don't have time now, but if you are interested, we can talk about and we can see how that can be done. Okay. Okay, so I'm mostly finished. A few things I wanted to point out. One can just a few variants. So you can restate all this in terms of continuous in continuous time, where there are various variants you can use. So here, instead of alignment, I'm using differential equations here, right? So I'm introducing. This is how I'm introducing the alignment rule. Okay, so the speed, the angular speed, is given by interaction with the other particles. This is how you do it in 2 dimensions, but maybe, so I put this first, but maybe this is a bit easier to visualize. So what you can see is that the rate of change of the velocity is related to, the average of the velocities of the other other particles. Okay. So that my velocity will change to try to point to the average. So this will move to try, will take my velocity to the direction of the average local velocity, okay? So you can think of it of this term as an interaction term, and then you can, well, you have to add this, technically you have to add, if you write it this way, you have to add this kind of Lagrange multiplier force that will keep the speed fixed, okay? Sorry. And you add a noise. And I wanted to write it this way because if you've seen the Langevin equation before, this is quite in the shape of a Langevin equation, right? So you can write the derivative of the velocity as an interaction force, and you can invent yourself a pseudo Hamiltonian, so that you can write this as a force. That's the derivative of some potential energy. And then you add the constraint force, the Lagrange multiplier, and the noise. And this really looks like a Langevin equation, if you've done that kind of thing in equilibrium statistical mechanics. And the thing is that, so to get this interaction, you have to write, you can write it, so this interaction can be written as the derivative of this interaction, which it looks quite reasonable because it's, just the way you write the ferromagnetic interaction between Heisenberg's spins, right? You just write Vi scalar Vj, okay? So in that sense, it's, so, and this explains why this strange sign here, whether this was coming from. It's coming from here, from just a scalar product. So this is a cosine here, and then the derivative will give you sine. So that's the reason. And so this behaves more or less like the Vickers model, which I showed before. It has some difference, some subtleties, but basically it does the same thing. It gives you for small noise, or in this context you can call it low temperature, because in the context of the Langevin equation, the amplitude of the noise is ruled by temperature. In this case, this temperature is not the physical temperature, it's just some parameter. But at low temperature, this will give you something that orders, goes from disorder to order. But I just a little bit in passing, but I mentioned this here, that if you see it written this way, what you see is a Langevin equation, but you see an overdamped Langevin equation. So there's no inertia here, okay? Don't be confused by the fact that this is the derivative of the velocity, which is effectively an acceleration. It's okay. It's true this is an acceleration, but remember that in these models, the interaction is not between positions, but between velocities, okay? So velocity is, V is the degree of freedom. And here I'm writing the derivative, the first time derivative of the degree of freedom, and this I'm equating to the force, okay? So that's an overdamped Langevin equation, an equation without inertia, okay? Which is not what Newton taught us, right? Newton said, no, you don't write the velocity proportional to the force. You write acceleration proportional to the force, okay? That's inertia, okay? When there's damping, we know in certain limits, we can ignore inertia and just write this. But it's important to keep in mind that this is the overdamped limit. And inertia, up to now, we don't know if it plays a role or not in this kinds of system. I will argue that it does in the last lecture, okay? So we are not using inertia now, but for certain kinds of system, you have to take it into account, okay? Okay, yes, this 1 minute here, by the way. But yes, okay. So let's finish. I just wanted to make the last comment. So let's keep about variants, the experiments. I will. Okay, I don't know what I'm here. So in the experiments, I will come back to this in the next lecture, but I will just point that in some cases, so in bird flocks, you kind of measure order and you have very ordered systems. In swarms, you will measure a very low polarization. And so if you just look at the polarization, you don't know if actually the system is interacting or not. Because here you say birds are ordered, okay, there must be some interaction. These are disorder. As far as we know, it could be just a gas, ideal gas of midges. So to answer whether there's interaction or not here, you have to go deeper than the order parameter, and you have to study correlations among velocities and among positions. Okay? So I'm saying this because next time I will start talking about correlation functions. I will give you an introduction about correlation functions. But this I will have to do because to interpret these experiments, we need to know about correlation functions. And I think that's something useful to know and something useful to use. So I will spend perhaps the whole lecture talking about correlation functions before going to the experiments. Okay? Because, again, but even so to finish here, even if you go in the case of the starlings, so you have the order parameter which tells you that the velocities are pointing in the same way, okay? But if you look at the fluctuations, you subtract the average, you still have quite a bit of structure here. So even if you look at the average, the fluctuations here, that's the correlations, are doing something interesting and something important, something you need to understand, okay? So that's the reason why we will study correlation functions next time. And then I can stop here. This brief comment, we can make it next time. So let's open for questions. And thank you.
So are there any questions for Tomás? Over there.
Yeah, it's over there.
So just at the end, where you presented that continuous version of the Vic-Check model, and you introduced that there was a term in the Langevin equation, the noise term, I'm sorry. So you have the noise term in the Langevin equation. Is this easy to translate this noise into that noise operator that you had before in the non-continuous version?
Depends on what you mean by easy. I mean, it is in the sense that since you are adding a constraint force here that will keep V0 fixed, it gives you the same effect. It will only affect the direction. Okay? If you want to compare, if you say this is a Gaussian noise and you want to compare the amplitude of the noise with the parameters you use in the noise, then it might get a little bit tricky. It's qualitatively the same. It might not be very easy to give an equivalence in the numbers of the parameters. But it's certainly true that the higher the temperature here, the less order you will have because the more you disrupt the alignment. Okay?
Yeah, I ask it because if I was aiming to simulate equations, I would like to discretize it in some way, and then I was wondering if I would just go back to the other versions of the model.
Not quite.
Okay.
Not exactly the same. Yeah, we can discuss this if you wish, but they're not the same.
Thank you. Any other questions?
I have one myself. So in natural scenarios for birds, for instance, you do not have periodic boundary conditions.
Right.
I mean, I'm not saying that the Earth is not flat, is flat, but
yeah.
in the life of the bird, it will not experience periodic boundary conditions. So in this scenario, you should need some sort of attraction between the particles to
absolutely
maintain the flock cohesive, right?
Yes. Strictly speaking, if you don't put boundary conditions, then the density is zero, so the flock evaporates slowly. So if you want to simulate without periodic boundary conditions, you have to put some attractive force. There are several variants of big shake that add these kind of things. You can add attraction, you can add hardcore repulsions. But in particular, to answer your question, for open boundary conditions, if you do not add a little bit of attraction that will keep the flock cohesive, then you will lose it. You will just, little by little evaporate.
Any other questions?
I think it was the previous slide with the model where they use the sign. Yeah, I think it was that one. I think it's no.
This one?
The sign. No, there was a sign.
A sign.
Yeah. No, it's not this one because you have a K, which I believe is like the. No, I'm not sure if it's a network.
I don't know. Here.
Yeah, that one. Yeah.
This one.
Yeah, you have the K on that theta.
Yes.
Is that K a network? Can you define it as any network?
Well, that's a good question. In principle, my intention was just doing this here. I wrote the K here. Okay, I was following these guys. I wrote this. So here, this simply is an indicator function, right? So if you are within the
yeah, it's a
radius,
right?
You can do the interaction network. You can define it as you want. The thing is, if you use a fixed interaction network, you basically lose the activity of the thing. So, I mean, if you just say particle 1 will always interact with particle 2, then the position becomes irrelevant. And so you're not doing active matter anymore. You're doing a model on the lattice, which is interesting, which can be like, Heisenberg, whatever, but you're not doing active matter. The point with active matter is that the interaction network will change in time depending on the positions. That's the feedback, position, interaction that more or less define or is crucial in the peculiarities of active matter. If you just define a network, yes, you can do it, but I would argue that it's not really, it's not active in the sense that the velocity loses its meaning as something that determines. Well, you can say that the velocity determines the position, but since the position is not connected to the interaction, then you can imagine that the velocity is just a vector, spin, whatever, right? And the model turns non-active, basically.
There is
Am I answering the question?
Okay, Tomás, thank you very much for the talk. I have a question. I understand that the spirit of this is to find the minimal mechanism that can explain the patterns that you have. But have there been tests about, for example, analyzing pictures in detail and checking whether when there is a change of motion, there is this kind of voting mechanism has been
This kind of
voting mechanism, like averaging and then deciding, or any kind of direct test on the biology to see whether this model makes sense or not?
I'm not sure how you could do that. I mean, the experiments I know of are you have the trajectories, and you measure trajectories, and so you can measure correlations. I wouldn't know how to do an experiment that's the Cavendish scale, right? I mean.
I don't know if it makes sense or not to do it, but actually now you can interact with the brain of a bird and change its direction telemetrically, and that will be a control way of inducing changes. You can do that.
Okay, yeah, that's interesting because I mentioned the Cavendish experiment because what you want is something that's with a single bird or with a couple of birds. Yeah, in that sort of experiments, yeah, I guess you have done this kind of things. Yeah, okay.
I don't do them, but I know groups that do. So I don't do them, but it's not difficult to change the direction with an implant. In a particular part of the brain, you can change the direction of a specific bird, and then you can induce or not. I mean, the kind of changes.
Okay, yeah, that's certainly is something interesting. The kind of experiments we have analyzed are collective experiments where you can measure correlations, and as you know, you measure correlations, cause and effect you can discuss, but you cannot measure in that kind of experiment. So yes, it's interesting would be very interesting to that. That said, it is also true that, well, you've said it yourself, but eventually, I mean, there are other models that propose other rules that eventually, at the larger scale, become alignment. So yes, but it would be nice to know how exactly the birds do it. Yeah, I agree.
So I would say one last question, and then we.
Thank you for the lecture. My question is, there's possible to get flocking transition without break the rotational symmetry, put an explicit alignment term in the equations? There's possible to get it, flocking transition without explicit alignment terms in the model?
With the alignment terms.
Because
no,
I did see some physical review letters the last years, Caprini, some talking about, for example, connect active particles with adhesion terms and increase the persistent time about in these particles, and they comment he found some flocking transition without explicit element term.
Yeah,
you
yes.
think it's possible?
Yeah, I think you can do it because so you can imagine more complicated interactions where, say, the birds want to stay together because they want to be cohesive, but then when they are about to collide, they will avoid this collision, and so they have to change their directions. So you can, without introducing explicit alignment, you can come up with mechanisms that along, over several time steps will eventually produce kind of collision where the two birds will move together. So you can get effective alignment without explicit rule in the model. Yes, I think you can. I've never done it, but yeah, I'm pretty confident you can do. I've seen some people attempting to do it, and I think it can be done. Yeah.
Just one comment about this. There is a comment paper after that one that you just mentioned, where they show that this flocking that emerges without explicit alignment is actually a finite size effect. So I think there is alignment, but there is no flocking transition in a sense.
Okay, well.
I don't know. I don't want to get into that, but
no, that's fine. The thing is that when you the discussion and the argument about what happens in the thermodynamic limit is always subtle, and more so in this case of these systems. But I could argue that since actual flocks are finite, then maybe it doesn't matter, because if that mechanism gives you, flocking for a finite flock, it's okay because flocks are finite. So I mean, I recognize that the question of what happens in the thermodynamic limit is interesting and is important, but I'm not willing to discard this model just because it doesn't do what you want in the thermodynamic limit, but it does for a pretty large system, right?
Okay, thank you. We thank the speaker again.
Okay, thank you very much.
And I don't know, Pablo, if you have any comments on what's next after the coffee break, because it's
yeah. So
different.
basically, we have coffee break now, about half an hour, and then we are going to go for the exercise sessions. As I mentioned before, each of you can decide a room to go. Each room will correspond to a different course that we had today, and there you will study or do exercises about that course. Okay? I don't know exactly, but they will be on that building of the coffee break, so we can just ask the guys over there. Okay?
Was a sign that said exercises somewhere? I cannot tell you where. There was a sign.
Yeah, there are 3 of them. Yeah. Thank you.